A surprising stretch. Heat makes solids grow. What happens when you heat things up? They get warmer, of course. But did you know that most solids also get bigger? That's right, they expand. This phenomenon, known as thermal expansion, might seem surprising at first. After all, we usually think of solids as rigid and unchanging. However, the world of atoms and molecules tells a different story. Imagine tiny balls, representing atoms connected by springs, representing the bonds between them. As we heat the solid, these tiny balls start vibrating faster and with a larger amplitude. This increased jiggling requires more space, causing the atoms to push each other slightly further apart. And guess what? The entire solid expands. This expansion happens in all directions, but we can break it down into three types: linear, aerial, and cubical expansion. Expansion in 1, 2, and 3 dimensions. It's all about the change. Let's start with linear expansion, which describes how much a material stretches in one dimension, its length. Imagine a metal rod getting longer when heated. The change in length, dl, is directly proportional to the original length, L, and the change in temperature, dt. A proportionality constant, called the coefficient of linear expansion, alpha, is specific to each material and tells us how much it expands for every degree Celsius or Fahrenheit increase in temperature. We can express this relationship with a simple equation, dl equals sine Al dt. Aerial expansion, on the other hand, describes how much a material expands in 2 dimensions, its area. Think of a metal sheet getting bigger when heated. Similarly, the change in area, dA, is directly proportional to the original area, A, and the change in temperature, dt, with the coefficient of aerial expansion, beta, being roughly twice the coefficient of linear expansion, beta 2a. Finally, cubical expansion describes how much a material expands in 3 dimensions, its volume. Imagine a metal cube swelling in size when heated. Again, the change in volume, dV, is directly proportional to the original volume, V, and the change in temperature, dt, with the coefficient of cubical expansion, gamma, being approximately 3 times the coefficient of linear expansion, gamma 3a. Not all solids are created equal. Coefficients of expansion. Now, not all materials expand at the same rate. Different materials have different coefficients of expansion, which means they react to temperature changes in their own unique ways. For instance, metals generally have higher coefficients of expansion than ceramics or glass. This difference arises from the strength of the bonds holding their atoms together. Metals, with weaker bonds, allow for greater atomic vibrations and thus expand more. Understanding these differences is crucial in many engineering applications. For example, bridges and buildings are designed with expansion joints to accommodate the expansion and contraction of materials due to temperature fluctuations. Expansion in action, from railroad tracks to thermostats. Thermal expansion plays a crucial role in various everyday applications. Remember those expansion joints in bridges? They prevent buckling and damage caused by the expansion of bridge materials in hot weather. Similarly, railroad tracks have gaps built in to accommodate expansion during summer heat, preventing them from warping and causing derailments. Thermostats, commonly found in homes and buildings, rely on the principle of thermal expansion to regulate temperature. A bimetallic strip, made by bonding 2 different metals with different coefficients of expansion, bends when heated or cooled. This bending action is used to open or close an electrical circuit, turning the heating or cooling system on or off as needed. From bridges to thermostats, thermal expansion is a fundamental phenomenon that impacts our lives in countless ways. Understanding its principles allows us to design safer structures, develop innovative technologies, and appreciate the intricate workings of the world around us.